Hey everybody, here we're going to be talking about section 4.4, that's other trigonometric functions. Okay. So, we've talked about the sine and cosine functions, how to get those values from the unit circle, and how to graph those functions on the xy plane. Here we're going to talk about the four other trigonometric functions. They are other four trig functions are tangent, cotangent, secant, and cosecant. Okay. So we've previously defined the these values. So let's just recall. So the definition: tangent of some value of x, let's say, is equal to sine of x divided by the cosine of x. Cotangent, we saw, is the reciprocal of tangent, so we just flip this, cosine over sine. Secant is the reciprocal of cosine, so 1 over cosine. And the cosecant is the reciprocal of sine, so 1 over sine x. So these identities that involve sines and cosines are going to help us to generate points from the unit circle onto the graphs of these functions. Okay? It's also going to help us attain values of these guys from the unit circle. So let's try an example. Let's find the tan of x, cotan of x, secant of x, and cosecant of x if x equals, let's do first pi over 2. Okay. So using our unit circle, we can generate these values by just plugging into these identities here. Okay. So let's look at the tangent of pi over 2. The tangent at pi over 2 is equivalent to the sine at pi over 2 divided by the cosine at pi over 2. So let's write that. Sine at pi over 2 divided by cosine at pi over 2. This is equal to, now let's go to our unit circle. So you can see here at the angle pi over 2, our sine is the y-coordinate, so that's 1 over 0, which is our cosine. And we know 1 over 0 is undefined. Can't divide by 0. So there must be something going on at x equals pi over 2 on the graph of tangent. You can probably guess, since we have a 0 down in the denominator, that this is going to make an asymptote on our graph. Let's look at the cotangent. Cotangent at pi over 2 is equal to the cosine at pi over 2 divided by the sine. So it's just the flip of tangent, reciprocal of tangent. So that would be 0 over 1, and that, of course, is 0. Lastly, the secant and cosecant CSC at pi over 2 That's CSC. Cosecant at pi over 2. So let's look. Secant is 1 divided by cosine, so that would be 1 over the cosine at pi over 2 is 0. Therefore, this is also undefined. So again, there must be something going on with the graph of secant when we get to the value of x, pi over 2. Cosecant is 1 over sine, so that would be 1 over the sine at pi over 2 is 1, so that is 1. All right. Let's try another one. Let's say we're going to do the same thing. Find tangent, cotangent, secant and cosecant of x when x is, let's do 3 pi over 4. So looking at our unit circle, we see the 3 pi over 4 angle is here. So all we need to focus in on are the point, the coordinates of the point for that angle. Okay. So we know that the tangent at 3 pi over 4 will be equal to the sine divided by the cosine. So let's pull off the sine. Sine is the positive square root of 2 over 2. Cosine is negative root 2 over 2. So it looks like square root of 2 over 2 divided by negative square root 2 over 2. Okay. So what's the square root of 2 over 2 divided by the negative square root of 2 over 2? Well, since these are the same values, this one's negative, we get negative 1. Okay. Cotangent at 3 pi over 4 is just the flip of that, so negative root 2 over 2 divided by root 2 over 2, which is also negative 1. Secant at 3 pi over 4 is 1 over the cosine, so that would be 1 over, the cosine there is negative root 2 over 2, which is, now remember when we divide by a fraction, it's the same thing as multiplying by the reciprocal of that fraction. So here we get negative 2 over root 2. And we can actually get this into an alternate form to make it a little easier to deal with. If we multiply, rule of thumb is that if there's a radical on the bottom, we can multiply the top and the bottom of this fraction by that radical. So square root of 2 times root 2, and get a new value for that. So on top we'll have negative 2 root 2 over the square root of 2 times the square root of 2 is 2. Therefore, this is equal to negative root 2. Cosecant at 3 pi over 4 is 1 over sine, so 1 over the square root of 2 over 2, which is 2 over root 2. Now let's rationalize that. So here again we'll multiply by that radical on top and bottom. So root 2 times root 2. This gives 2 root 2 over root 2 times root 2 is 2. So we get positive square root of 2. Let's do one more of those. do the same thing, but with a different angle. Find the tangent, cotangent, secant, and cosecant of x when x is, let's do 7 pi over 6. Alright, so let's start with our tangent. Tangent at 7 pi over 6 equals the sine at 7 pi over 6 divided by the cosine at 7 pi over 6. So let's go to our unit circle and find those values. So the sine at 7 pi over 6 is -1/2 divided by the cosine there, which is -√3 over 2. -√3 over 2. Okay? Now, to simplify this, of course, we can just multiply by the reciprocal of the bottom fraction. So this will be equal to -1/2 times the flip of this, so -2 over √3. Now we see a negative times a negative is going to give us a positive, and these 2's are going to cancel each other out. So what we have is 1 over the square root of 3, which again we can rationalize. So if we multiply by that radical at the bottom, times the square root of 3 times the square root of 3, the tangent at 7 pi over 6 is the square root of 3 over 3. Now for cotangent at 7 pi over 6, we could go through this process, but since we already know what the tangent is there, all we need to do is just take its reciprocal. So we're going to take this fraction and just flip it over. So we know the cotan there is going to be 3 over √3. And again, we can rationalize. So square root of 3 times square root of 3. So we see we get 3√3 over 3. Those 3's will cancel. So just the square root of 3. Secant at 7 pi over 6 is 1 over the cosine. Cosine is -√3 over 2. So again, multiplying by the reciprocal, so it's like 1 times -2 over √3, or -2 over √3. And rationalize. So I get -2 √3 over 3. Lastly, our cosecant, 7 pi over 6, is 1 over -1/2, which is 1 times -2 over 1, or -2. That one's easy. Alright, now that we are able to find points associated with different angles, we can graph these functions just like we did with sine and cosine. We'll also investigate the periodicity of each of the functions and some other things associated with them. Okay? So let's look at the graphs of tangent and cotangent. So first we'll do tangent. Graph of basic tangent. Let's say y equals tan x. Okay. So what we want to do is create a table of values for the tangent function. We'll plot them, and then we'll investigate some things about its graph. Okay. So let's do a XY coordinate table here. X and Y. Do it long ways to start. And let's just go around the unit circle, getting those values of tangent. Okay. So I'm going to use 0 here, and then pi over 2, pi, 3 pi over 2, and 2 pi. And I've left some space just in case we need to fill in some additional angles. All right, so let's go around and collect the tangents here. It's a little different because we can't really see the tangent here, so we're going to have to do sine divided by cosine to get those values. Okay, so let's look at 0. So 0, we know the sine is 0 and the cosine is 1. So 0 divided by 1 is 0. So we know that the tangent of 0 is 0. Now at pi over 2, the sine is 1 and the cosine is 0. So 1 divided by 0 is undefined. Let's say UND there. At pi, we'll have 0 divided by -1, which is also 0. And at 3 pi over 2, -1 divided by 0 is undefined again. And then at 2 pi, it's the same point as 0, so 0 there. So let's see what we have so far. It looks like we don't have much of anything at all, but we'll get some additional angles here in a second. Get some more points. Okay. So here's X, here's Y. This is 2 pi. Pi over 2, 3 pi over 2. And we'll do a negative side too. And we don't really have any information about the y coordinates at this point, but we do have some information. So we know that at anywhere where it's undefined, we don't have a value there. So what happens on the graph is that we have an asymptote. So at pi over 2 and 3 pi over 2, we're going to have asymptotes. So let's draw those in as dotted lines. So we're going to have some asymptotes, and let's think about where the next asymptote will occur. On this negative side, if we look at the pattern here, it's every kind of every pi units will have a asymptote. So our next asymptote will occur at negative pi over 2. And then again at negative 3 pi over 2 if we continue that pattern. Now as for the values of our function, we know at 0 it's 0, so we have a point at the origin. We have a point at pi that has a y-coordinate of 0, and then again at 2 pi. So it looks like in this very center of the asymptotes we'll have a point. So it looks like we'll have a point here as well, and here as well. But what is the graph doing? So let's think about it. We may need to actually get a couple of additional points in between these guys of our table. So let's try pi over 4. So at pi over 4, the values of sine and cosine are the same number. So when we divide them, we'll get 1, right? Root 2 over 2 divided by itself is 1. The next pi over 4 angle would be 3 pi over 4. So we go to 3 pi over 4. We have the same makeup of points, except one of them is negative. So root 2 over 2 divided by negative root 2 over 2 will give us negative 1. We go to the next pi over 4 angle. It's 5 pi over 4. They're the same value again. So that gives us a y-coordinate of 1. And then we have 3 pi over 2. The next one's 7 pi over 4. The tangent would be negative root 2 over 2 divided by root 2 over 2. That's negative 1. So let's see if this kind of sheds some light on the graph here. So that pi over 4, which is our halfway point here, pi over 4, we'll have 1. Then at 3 pi over 4, which is here, in between pi over 2 and pi, we have a negative 1. At 5 pi over 4, we have a positive 1 again. And at 7 pi over 4, we have negative 1 again. So we can kind of see a trend building here. So if we notice at negative pi over 4, looks like we'll have a negative 1. That seems to be the trend. That's absolutely right. So here, in between here, we'd have a positive 1 and a negative 1. And a positive 1 and a negative 1. And then all the way over here, we'll have a positive 1. So we can kind of see the graph of the tangent function shaping up. So here we have these asymptotes we know we can't cross. So the first bit of the tangent function kind of looks like that. And then it repeats itself because these are all periodic functions. So we have another leg of it there. And another one there. Of course, there would be an asymptote over here. And another one there. And another one there. So the tangent function does not resemble a wave like sine and cosine, but it kind of looks like a x to the third power kind of polynomial. One thing we can look at here is the period. Does the period seem to be the same? Well, for the sine and cosine, the period was 2 pi in each case. In this function, we can see that it repeats itself actually between negative pi over 2 and pi over 2. So this distance here is pi. So what we want to say down here is the period of y equals tan x is pi instead of 2 pi, right? We can also look at the x-intercepts and where the asymptotes occur, right? So let's look at that. The x-intercepts happen when x is what number? So it looks like we have an x-intercept at 0, at pi, at 2 pi. There would be another one at 3 pi and 4 pi and so on and so forth. So all the x-intercepts we can represent as n pi, where n goes from negative 1, 0, 1, 2, Asymptotes occur when x is, well, let's see. Do we see a pattern here? So pi over 2, 1 pi over 2, 3 pi over 2. The next one would be 5 pi over 2. Negative 1 pi over 2, negative 3 pi over 2. So it looks like the asymptotes are occurring at all odd multiples of pi over 2. So just like with our cosine, 2n plus 1, that's our odd number, times pi over 2. Again, n is going from negative 1, 0, 1, 2, okay. All right, so now let's look at the graph of cotan. So the graph of cotangent. Y equals cotan x. Okay. So this one's not going to be too hard. We don't have to reinvent the wheel. All we need to do is take reciprocals of the previous values. So let's put in those numbers there. 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. These are just the values from the tangent table that we made previously. Okay. Now what we're going to do is just take reciprocals of the values of y, because we know that tangent and cotangent are reciprocals of one another. So all we need to do is just flip over the numbers and see what we get, right? So the reciprocal of 0 is undefined, right? So 0 divided by 1, if we flip that, that would be 1 divided by 0. So anywhere we have a 0 on the tangent curve, we have an undefined on the cotangent curve. The reciprocal of 1 is simply 1. The reciprocal of undefined, so remember we did got an undefined result, that was 1 over 0. So the reciprocal would be 0 over 1, or 0. The reciprocal of negative 1 is negative 1. The reciprocal of 0 is undefined. Again, I'm getting all of these from our tangent table here, right? I'm just doing the reciprocal of each of these values and filling in our cotangent values. So at 5 pi over 4, tangent was 1. The reciprocal of 1 is 1. 3 pi over 2 was undefined, so we'll get a 0 again. And a negative 1 and an undefined. Alright, so let's scale. Like we did before. Here's 1 and negative 1. And 2 pi, pi over 2, 3 pi over 2. And do the same in the reverse. Negative 2 pi, negative pi over 2, and negative 3 pi over 2. Alright, so let's put in our asymptotes first. So at 0 we have undefined, so we know at 0 we'll have an asymptote there. At pi, and at 2 pi. Okay. So let's guess to see where the 1 happens over here. So it looks like the asymptotes are spanning about every pi units. So our asymptote in this direction would be at negative pi, and another one at negative 2 pi, and another one at negative 3 pi, and so on and so forth, right? All right. Now, let's put in our points. So it looks like our X-intercepts happen at all of the pi over 2. So pi over 2, 3 pi over 2, any middle point in those intervals. Now let's graph our pi over 4. So at pi over 4, we're at 1. At 3 pi over 4, that's in between pi over 2 and pi, we're at negative 1. So we can see a kind of a similar trend, just kind of in the reverse direction. So one period of the cotan function looks something like that. So we'd have the same trend over and over again. So here we would have a 1. Here we would have a negative 1. You would get another copy of that. Another period of the cotan function. So over here, we would have a 1 here, a negative 1 there. Again, we can't cross these asymptotes. Okay. So cotan looks like it's a reflection and a shift of the tangent function. So what's the period here? So the period of cotangent is, well, when does it start to repeat itself? It repeats itself after every pi units. So the period is pi, again. The x-intercepts happen when x is equal to, well, let's see here, at pi over 2, 3 pi over 2, 5 pi over 2, so it's odd multiples of pi over 2 again. So 2n plus 1, pi over 2. Of course, n goes from -1, 0, 1, da, 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 right? Asymptotes occur at all the pi's, right? All the whole number multiples of pi. So that would be n pi. N is the same there. Okay. All right, so let's get out our handy-dandy properties of trig graphs, and let's just fill those in, okay? So we want to fill in our tangent column. We want the domain. We haven't really talked about that. So let's see here. Here's our tangent function. Is the domain all real numbers, like sine and cosine? Well, no, it's not, right? So it doesn't have, it can't have x values at the odd multiples of pi over 2. So here's how we're going to do the domain for that. So we're going to say that that is we're going to do it in set notation. So we'll say that x such that x is not equal to any odd multiple of pi over 2. So 2n plus 1 pi over 2. Okay. Let's look at the range. So if we look at our tangent graph, looks like the range is negative infinity to positive infinity. So that would be all reals. The period was pi. Now let's determine if it's even or odd. So if we fold this across the y-axis, we don't get a match, so it's not even. But if we revolve it around the origin, we get exactly the same looking graph. So this function is odd. The zeros happened at n pi. And of course the asymptotes occurred where the domain discontinuities were, so when x was 2n plus 1 pi over 2. For cotangent, you see that the domain excludes all the whole number elements, whole number multiples of pi. So we'll say the domain is the set of all x's such that x cannot be equal to n pi. Okay. The range, if you look, is all reals, right? Period was pi. Now let's look at even or odd. Let's look at, if we fold this across the y-axis, do we get a match? Not quite. This would have to have some matching thing here, right? So, no. If we turn it upside down, do we get the exact same looking graph? We do. Therefore, this function is also odd. The zeros occurred at odd multiples of pi, so x equals 2n plus 1 pi over 2. And the the asymptotes occurred at whole number multiples of pi. Okay. Now let's look at secant and cosecant. Then we'll deal with transformations. So the graph of secant, y equals secant x. See what this guy looks like. Alright, so let's build a table here, x's and y's. And we'll go for the easy ones first, and we'll fill in if we need to. So let's do 0, pi over 2, pi, 3 pi over 2, and 2 pi. Alright, recall that the secant, remember, secant is 1 over cosine. 1 over cosine. So we're going to take and find those values. So at 0, let's look at what we have. At 0, the cosine is 1, and 1 divided by 1 is 1. At pi over 2, the cosine is 0, and 1 over 0 is undefined. At pi, cosine is negative 1. 1 over negative 1 is negative 1. At 3 or at pi over 2, it's again 0, so we get another undefined. And 2 pi is the same as 0, so 1. Okay. So let's look. X and y, 2 pi, pi over 2, 3 pi over 2. And 1. Let's do our negative side as well. Alright, so let's plot what we have. So we see that there are asymptotes at pi over 2 and 3 pi over 2. So let's graph those in there. Pi over 2 and 3 pi over 2. So it looks like they're happening every pi units as well. So our next asymptote will be at negative pi over 2 and negative 3 pi over 2. Alright, at 0 we have 1. At pi, we have negative 1. And at 2 pi, positive 1. Alright. Now, it looks like we don't have much information, like, or do we have any intercepts here? What's going on? So let's fill in some points between these guys. We'll use our pi over 4s and see what we get there. So at pi over 4, let's see what we get. We have 1 over the square root of 2. So 1 over the square root of 2. So let's just cheat a little bit. 1 divided by root 2 over 2. Get an approximation. So it's about 1.4 approximately. Okay, approximately 1.4. And 3 pi over 4. At 3 pi over 4, the cosine is negative root 2 over 2. So 1 over negative root 2 over 2. would be approximately negative 1.4. Then going around, and next is 5 pi over 4. The cosine is again negative root 2 over 2, so that's the same, about negative 1.4. And at 7 pi over 4, cosine is back to positive root 2 over 2, so that's positive 1.4. Okay. So let's see what we get. So at pi over 4, it's about 1.4, so maybe right about there. So we're going to make little marks, halfway marks for our pi over 4s. At 3 pi over 4, we get negative 1.4. And 5 pi over 4, we get negative 1.4. And at 7 pi over 4, we get positive 1.4 again. So you can see the graph of this section shaping up. Looks kind of like a parabola that follows those asymptotes downward. So let's make some guesses about what's here. We actually can just calculate it. At negative pi over 4, negative pi over 4 is the same thing as 7 pi over 4. It's coterminal with that angle. So it's going to have the same point at 7 pi over 4. So 1.4 there. All right. So that means on the other side of this one, we would have something like that. Okay. So you can see it kind of flip-flops with these kind of parabolic shapes. So over here, we're going to have the same thing, but just downward. And then here, we'll have 1, upward. All right. So let's look at the period. So when does it start to repeat itself? Well, notice it repeats after when we get back to the upward turning one, right? So we go up, down, and then it starts to repeat up, down, up, down, up, down. So if we look, this distance here is, well, that's 3 pi over 2 and another pi over 2. That's 4 pi over 2 or 2 pi. The period of secant is 2 pi. Where the X-intercepts occur at nowhere, so this is not applicable, right? They have no X-intercepts for the basic one. And asymptotes happen when X is equal to odd multiples of pi over 2. Let's look at the cosecant curve, and then we'll fill in our table. We'll complete our property table. Graph of cosecant y equals CSCX. Unfortunately, the secant and cosecant are not reciprocals of one another, so we're going to need to generate another table here. X, Y. Let's put in our regulars, 0 pi over 2 pi, 3 pi over 2, 2 pi. And then we'll start to go around the unit circle and collect those values. So remember that cosecant is equivalent to 1 over sine. So at 0, sine is 0, so undefined. At pi over 2, sine is 1, so cosecant is also 1. And at pi, sine is 0, so we get undefined again. At 3 pi over 2, we're at negative 1, so cosecant will be negative 1 as well. And we're back to undefined. So let's see if we can generate this graph. All right, so let's scale our axes like normal. X and Y. And let's put in our asymptotes. Asymptotes occur at 0, pi, and 2 pi, so all the whole multiples of pi there. So we get another one at negative pi and negative 2 pi. Follow that pattern. So secant, cosecant pi over 2 is 1. At 3 pi over 2, it's negative 1, so we get the same kind of result here. So if we were to have another one, let's say that's 5 pi over 2, and we get a 1 there also. Okay. So it looks like we would have a negative 1 at negative pi over 2, and then another positive 1, and then another negative 1 over here. Right? So it's the same idea. So we have these upward kind of facing parabolas, downward facing parabolas, alternating. Of course, we could check that, but we know that's basically what's going to happen. Okay. So the period of this function, when does it start to repeat itself? Well, it's got to go up, down, up, so it repeats after 2 pi units. The X-intercepts occur at nowhere, so that's not applicable. And asymptotes occur at whole number multiples of pi, so n pi. All right, so let's fill in our table. We'll be done with that. All right, so first up is secant, the domain. So let's look at the domain of secant. It's everywhere it doesn't have an asymptote, so that's odd numbered multiples of pi over 2. So all the x's such that x cannot be an odd multiple of pi over 2. The range, let's look at the range for secant. So here we have values up until negative 1, then we skip out on all the values between negative 1 and 1, and then pick up again there. So this is kind of broken up into 2 pieces. So it'll be negative infinity to negative 1 inclusive, and 1 to positive infinity. Period is 2 pi. Now let's think odd or even. If I take this and fold it across the y-axis, do you get a perfect match? We do. Therefore, it is an even function. The zeros happened at nowhere, not applicable. And the asymptotes occurred at odd multiples of pi over 2. Last up, cosecant. If we look, the domain happens, the domain restrictions are any whole number multiple of pi over 2. So all the x's such that x can't be n pi. The range is the same as secant, so negative infinity to negative 1 and 1 to infinity. The period was 2 pi. We know that 0 is not applicable, and x is n pi for asymptotes. Now, is it even or odd? Well, if we look here, if we fold it across the y-axis, do we get a match? And we don't, because we would need something here to match up with this guy here. If we spin it around 180 degrees, do we get the same looking graph? We do. Therefore, this is an odd function. Okay. All right, so there is our completed table of trig graph properties. That's a nice thing to have. Now let's look at using a few transformations to graph some variations. So transformations of tangent, cotan, secant, and cosecant. So we want to graph y equals tangent of 2x. Okay. So recall that the b value here is going to either horizontally stretch or compress the graph of tangent. So in this case, this represents a horizontal compression. Okay. So all we need to do is generate those values using transformations. Okay. So let's make a table of values for tangent. The basic tangent parent function. So y equals tangent x. So the basic tangent points, let's see. So note that the period of the tangent function and cotangent function are pi. So let's go 0 to pi instead of 2 pi. And let's count by pi over 4. So pi over 4, pi over 2, 3 pi over 4, and then pi. Because we get one period of the tangent function in that interval. Okay. So if we look back, the tangent function is 0 at 0. It's 1 at pi over 4. Undefined at pi over 2. Negative 1 at 3 pi over 4. And then 0 again at pi. So now if we do our transformation, note here we always do the opposite effect if we're grouped in with the x here. So we're going to divide all the x values by 2. So I'm going to divide all those x values by 2. And y is going to stay the same. So 0 divided by 2 is 0. Pi over 4 divided by pi over 4 divided by 2 is pi over 8. Pi over 2 divided by 2 is pi over 4. 3 pi over 4 divided by 2 is 3 pi over 8. And pi divided by 2 is pi over 2. All of our other values will stay the same. 0, 1, undefined, negative 1, and 0. Okay. So let's graph that. All right, so we're just scaling these. 2 pi, pi over 2, 3 pi over 2. I'm going to put some marks here for our pi over 4s as well. So it looks like we have an asymptote at pi over 4. And we can start filling in some values. So at 0, we're at 0. At pi over 8, so that's in halfway between pi over 4 and 0, we're at 1. At 3 pi over 8, so that would be halfway here, we have a negative 1. And at pi over 2, we're at 0 again. So here we have one full period of the, or one half period here, half period there. So we know at the next half step, we would have a 1. And then another asymptote. Okay. So we get a picture of the tangent function, kind of horizontally compressed. We know that we would have another asymptote at pi over 4 here. So let's scale that, negative pi over 2, pi, negative pi over 2, there's pi over 4. So we have another asymptote there. And of course a matching point kind of halfway in between. Something like that. Okay. So you can see what's happened from, here's the original tangent function. And when we horizontally compress it, it kind of just shrinks it inward horizontally. Let's look at the period here. Period. Well, here we have shrunken the period to be within this range here. So note that if we look back at the table, our original period was 0 to pi. Now we get a full revolution in pi over 2 units, right? So the period is pi over 2. The X-intercepts, let's see, those happen at 0, pi over 2. The next one would be at pi, right? So we'd have another value there, another asymptote here, and a corresponding curve there. So it looks like it happens at 0, pi over 2, pi, 3 pi over 2, again at 2 pi. This is at all multiples of pi over 2. Therefore, X-intercepts occur when X is n pi over 2. Finally, our asymptotes occur when X is equal to, now here, this would be at pi over 4. This is at 3 pi over 4 and 5 pi over 4. So at 1 pi over 4, 3 pi over 4, and 5 pi over 4. Therefore, those are all odd multiples of pi over 4. Let's try one involving secants and cosecants. So in a graph, let's do y equals -1 plus the secant of x minus 2 pi. Okay. So let's recall our table for secant. So let's do our parent function, y equals secant. Remember that the period was 2 pi, so let's go to 2 pi by pi over 2. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Again, this is going to be a little different because we saw in the basic graph that it started to repeat after 2 pi units rather than pi units. If we look back at our results for secant, we had 1 when x was 0, and then an asymptote, undefined, then -1, then undefined again, then 1. Okay. So when we do our transformation, let's think about what we're seeing in the equation here. So we know this -1 out front here, you know, that this is kind of like d, right? So we can rewrite this as secant x minus 2 pi minus or plus -1, let's say. That's the same thing. So this is a vertical shift. And here we have a horizontal shift. There's only a 1 in front here, so there's no factoring that needs to happen. So we have a horizontal shift of right 2 pi units, and the vertical shift down 1. Okay? So let's make our table of values for a transformed function. So if I'm shifting to the right 2 pi units, I'm going to add 2 pi to all my x's. And vertically shifting down 1, I'm going to subtract 1 from all my y's. So let's do that. 0 plus 2 pi is 2 pi. 1/2 pi plus 2 pi is 5 pi over 2. Pi plus 2 pi is 3 pi. 3 pi over 2 plus 2 pi is 7 pi over 2. And 2 pi plus 2 pi is 4 pi. And here we're going to subtract 1 from all the y's. So 1 minus 1 is 0. An undefined value minus 1 is still just undefined. Can't do anything there. -1 minus 1 is -2. Again, undefined. And 1 minus 1 is 0. So let's go ahead and graph our points here. So note that this time our x's go to 4 pi, so I'm going to start that over here, 4 pi, and then 2 pi, and pi over 2, 3 pi over 2, 3 pi, 5 pi over 2, 7 pi over 2. And we get up to, so 1 there, and then -2. Let's put our asymptotes in. So at 5 pi over 2, there's 1. And at 7 pi over 2. So let's think about where the other ones would be. So it's every pi units here. So at 3 pi over 2 and at pi over 2. Alright, now at 2 pi we're at 0. At 3 pi we're at -2. And at 4 pi we're at 0 again. So at pi we would be at -2. So recall that these are like up and down turning parabolas, so we know that this function is going to look like something like this. All right, we would have another one over here. Something like that. All right, let's look at the period and any intercepts that we have. The period seems to be 2 pi still. X-intercepts, we have some X-intercepts this time. That's when X is, so let's look, 0, 2 pi, 4 pi, the next one would be 6 pi. So these are all even multiples of pi. So that would be 2n pi. Again, 2n gives us any even number for when n is -1, 0, 1, 2, so on and so forth. And finally, our asymptotes occur at x equals, looks like odd multiples of pi over 2. 2n plus 1